Water is, this is a related rates problem. We have water is draining at a rate of 48 pi cubic feet every second. From the vertex at the bottom of a conical tank, it's a cone, and the vertex is at the bottom. That's the point of the tank. It's an inverted cone, like the picture we have here. The water's leaking out, and so the water level is decreasing. The tank has a radius of 20 because its diameter is 40 and its height is 60. So this is the picture that we have here that represents this this first sentence here. When they say that the water is draining out at a rate of 48 pi, this is how volume is changing. This is dV dt. Negative 48 pi. It's decreasing. Okay. Letter A. Find an expression for the volume of water in the tank in terms of its radius at the surface of the water. And so, in letter A, its volume is equal to, for a cone, volume for a cone is 1/3 pi r squared h. And r and h are related to each other. And we want the volume formula in letter A. We want the volume formula, but only in terms of the radius. We want volume as a function of r, so we need h not to be involved in this formula, and so we have to figure out how. We have to find out how r relates to h. Find the relationship between r and h. And what it is we use similar triangles. There's two triangles here. There's the big triangle and then there's the smaller triangle. And what we have is that in the bigger triangle, oh, that's terrible. In the bigger triangle, we have, oh, okay, let me just go ahead and draw the smaller one while I'm at it. Okay, so in the bigger triangle, we have the 20 to 60, and in the smaller triangle, we have r to h. I guess I can't erase that. Let's try to do a better job. Okay, so here we go. Okay, so they are similar triangles. They have the same angles, and so we have 20 is to 60 as r is to h. The ratio of the legs is equal to the ratio of the legs in the other triangle. And this tells us then that 20h is 60r, or that h is 3 times r. We'll use that later. This volume formula in terms of r becomes 1/3 pi r squared, and then h is 3r. So these 3's cancel, and your volume as a function of r is 1/3 pi, I'm sorry, the 3 and the 1/3 cancel, and so we just end up with pi r cubed. So that's the answer to A. Now to B, using this formula, in letter B, we say, well, at what rate is the radius of the water in the tank shrinking? So, in letter B, they want us to find dr dt. We know dv dt, so we start with this equation and we take dv dt, and it's going to be equal to 3 pi r squared dr dt. We know dv dt is negative 48 pi. At the instance when the radius is 16, they tell us that r is 16. That's our snapshot. R is 16. So right in here we plug a 16 in. Okay, and we can figure out what dr dt is. 16 times 3, 16 squared, I'm sorry. So negative 48 pi is 3 pi times 16 times 16, I'll write it like that on purpose, times dr dt. And this is 48 pi. And so what happens is we go and divide. We end up with 48 pi times 16. I'll write like that on purpose. So when I go to divide by that, I can just easily cancel. I'm trying to solve for dr dt. I divide by this, what's multiplied by dr dt, and we can see how we cancel. So dr dt, oops. So dr dt is negative 1 over 16. What units? Feet per second. That's how R is changing. So it's a three-part question. Here's A. Here's B. And now part C. Part C is, okay, what about dh dt? Part C says, how fast is the height of the water in the tank dropping at that same instant? Well, we know how h and r are related to each other. This equation right here gives the relationship between h and r. If you know how h and r are related, then you know how their derivatives are related. If h is equal to 3r, then you take the derivative and you'll get that dh dt. H is changing with time. Dh dt is 3 times dr dt. So whatever you get for dr dt, just multiply it by 3. And so that's why we end up with dh dt being 3 times negative 1 over 16 from part B. Okay, so dh dt is negative 3 over 16. Units, feet per second. Okay, great. So the first part was a setup. They wanted you to write volume only in terms of R. You didn't have to do that, but they set the problem up that way, and that made it easier to do part B. Without that, we could definitely do the derivative of the cone equation in general with R's and H's in there. Later we would find out anyway that H is related to R, so this problem sets you up to solve it in an easier way.